Welcome to the chapter on fluids. When we talk about fluids, we can either talk about fluid statics, which refers to fluids that are stationary, or fluid dynamics, which is fluids in motion. So the first part of the chapter will be on fluid statics, where we talk about things like fluid pressure, buoyancy, variation of pressure with depth, and then we talk about fluid dynamics, the motion of fluids, involving Bernoulli's equation, the continuity equation, and this is applicable to breathing and circulatory systems and important topics in biology. When we look at states of matter, we either have solids, liquids, or gases. Well, I guess there's plasma too. In the case of a solid, you have a binding energy between the molecules is greater than the thermal energy. So we take the thermal energy as proportional to the temperature T times the Boltzmann constant. For a gas, the binding energy is much less than the thermal energy, and the molecules are free to move around inside of a gas. The liquid is somewhere in between, where the binding energy is proportional on the order of the thermal energy. So fluids are kind of rare in the solar system. For example, on Earth we have liquid water, but we don't really find a lot of liquids on other solar system bodies, except maybe for the moon of Titan, where we have liquid hydrocarbon lakes on Titan. So a fluid can be both a liquid and a gas. So breathing, circulatory systems, these are all examples of fluids. The pressure of a fluid is given by the force that the fluid exerts divided by the area. Now the force will always be perpendicular to whatever body you have, so there's no shear. We're assuming there's no shear forces here that would be tangential to a surface. If you want a small pressure and you have a large force, you just get a large area. For example, these snowshoes would exert a small pressure on the snow so you don't fall through. However, if you have a very small area, you can get a quite large pressure. And these type of shoes, these stiletto heels, used to be not allowed in grocery stores. You crack the tile. Pressure is a scalar quantity. It's proportional to the magnitude of the force. The units of pressure are the Pascal after Blaise Pascal. 1 Pascal is a Newton per square meter. In those units, the atmospheric pressure is enormous. The atmospheric pressure is roughly 10 to the 5th Pascal, or 1.013 times 10 to the 5th Pascal. That's 1 atmosphere. So the atmosphere extends above us quite a large distance, and we are in equilibrium essentially at the surface. You can measure pressure with a contraption like this. If you have a vacuum container with a spring and a force applied to this plunger, we know from Hooke's law that the spring will stretch proportional to the force. F is equal to kx. And if we know the area, we can just divide the force by the area to get the pressure. So this is a very simple pressure gauge, and you could calibrate this. Now, if it's calibrated to measure 0 at the surface, then we call that the gauge pressure. If it's also calibrated to measure the atmospheric pressure, we call that the absolute pressure. In general, the pressure as a function of depth will be proportional to the height or the depth in the fluid, also to the gravitational constant and the density of the fluid. If the liquid is open to atmosphere, P naught is the atmospheric pressure. The pressure has to be the same at all points, having the same depth, independent of the shape of the container. So even if you had a crazy shaped container like this, the pressure at A would have to be equal to the pressure at B.